Okay, so today I'm gonna be I'm making another video. I kind of wanted to make a video about something I haven't really covered. I might have touched in another video. It has to do with calculus 3 and maybe 4, if you want to consider that, but it's gradients. So gradients are an extremely practical thing. Like when you study calculus in school, you might think, okay, what's the practical application of this? It doesn't really make any sense. Well, gradients are the exception. Gradients kind of, you can, a normal person can kind of notice why is this important. So a gradient is the greatest change from a point, the greatest rate of change from a point. So let's say there's a hiker. Let's say this dot is the hiker, and he's in the um, basin of a mountain, and every direction goes up. Okay, and he wants to find what's the fastest way I can get up. Well, that direction expressed as a vector, so an xy, that direction will be the gradient because that's the direction of the fastest rate of change from his position. So this is useful in a lot of scenarios. It's useful for computer programming, practical applications like this, mechanical engineering, lot of stuff, calculus, obviously. Um, so there's actually a very easy way to like find a gradient. So a gradient, let's say we have some equation in 3 space. So let's say x, y, z. I'm going to do it in the largest dimensions possible, and then I'll cut down. So in x, y, z, we have some equation ax plus by plus cz. These are raised to the m, n, m, and l. Well, the gradient, which is expressed as like a delta, maybe shaded a little here, I don't know, and of xyz is going to be the partial derivative of f with respect to x in the I, and then, yeah, plus the partial derivative of f with respect to y in the j, plus the partial derivative of f in the z with respect to k. So if you're watching this video, you probably know what partial derivatives are. If not, I recommend clicking off and watching one of my previous videos on partial derivatives and how to solve them. But essentially, the partial derivative is just in a 3 space, it's the derivative of that function with respect to one variable. So the partial derivative of f with respect to x would then just be nax to the n minus 1 for some case like this. Like, let's say it's a perfect case and they're all raised to exponents with just coefficients, so it would be nax n minus 1. Following the same train of logic, at the partial derivative of f with respect to y would then be um, uh, I have this backwards, by the way. My notation is backwards. It should be flipped. I'm sorry that I wrote it that way. I wrote the first one wrong and then kind of followed it. So, so the partial derivative of it should be y with respect to f. Now is going to be b times m y minus m. Now the partial derivative of c with respect to f is going to be cl to the z L minus 1. So what does this really tell us? So now when we plug this into the gradient, I'm just going to write the gradient as the symbol because I'm lazy and don't want to have to write this equation. So I'll write it as gradient of f is equal to the partial derivative of x, which is nax n minus 1 in the I, and then plus bmym minus 1 in the j, plus CLZ to the L minus 1 in the K. And this right here for anything in this form will give you the fastest rate of change at what direction. So let's say we plug numbers in and we get, like, let's say we're trying to find the, and I'm not using a function in this form. Like, I'm just saying, let's say your math teacher gives you some gradient, um, capital F, to find the gradient of at 0.41, and you get, by the way, when you plug the numbers in, you'll get like some constant in front of x, some constant in front of y, some constant in front of z, unless it's some functional gradient, because it can't be. So, or it is until you plug a point in. But let's say you plug this in and you get 4i plus 5j plus 6z. Well, what does this mean? So this means that if we head in the direction of this point, wherever this is located, this is the fastest rate of change for us to increase. So wherever we're based at, so it's saying at this 0.41, heading this direction is the fastest possible rate of change. It's kind of spooky how it works every time. It's a long derivation for it, but it does work. So it's essentially, it's just solving the, it's finding the sharpest derivative at that point, and it's doing it in a very efficient manner. So let's say we had f of x, y, z, so I can show an example real quick, is equal to 4x plus 3y plus z. So partial derivative with respect to x, I keep writing it backwards, sorry. I mixed up notation. Is equal to 4. Partial derivative with, I'm just going to keep it the same since I've done it the whole video, but partial derivative with f with respect to y is 3. Partial derivative of f with respect to z is equal to 1. Now, when we go in here and we plug this in, we get the gradient of f is equal to 4i plus 3j plus 1k, which I'm just going to write as k. So what does this tell us? So you've kind of got to think about this, because this is essentially a line in free space. So since this is a line in free space, think about it. A line has that's not a line. A line has a slope that is not changing. It has one singular slope. So when we try to find the gradient, we found these partial derivatives, and they were all constant. What does that mean? That means that for any x, y we plug in there, the codomain of this point for the gradient is going to be this. The gradient doesn't change. That makes sense because it's a line. So the slope is not changing. So the fastest rate of change at any point is going to be straightforward along the line, because you can't leave the line. So this is the gradient at any point. It's kind of cool. So yeah, I think that's a cool example. If you have any questions, if I didn't cover anything or I messed up, just let me know in the comments. And yeah, thanks for watching.